Every heartbeat begins with ions flooding across microscopic channels in a single cell membrane. This tiny voltage shift is the basic unit of a coordinated wave involving billions of cells firing in rapid succession. The surface electrocardiogram captures the aggregate, delayed echo of these action potentials as they wash across the cardiac muscle. This complex electrical storm is usually presented on a stark two-dimensional grid. The challenge for the clinician is bridging the gap between this flat piece of paper and a living three-dimensional organ. Reading an ECG effectively requires moving past rote memorization of wave shapes. You have to reconstruct the three-dimensional geometry of the heart using the rules of vector physics. To accurately interpret these lines, we must synthesize microscopic cellular biology with spatial geometry. This diagram plots the action potentials of specific cardiac structures against the aggregate surface ECG. If we look at the top right, the heartbeat originates at the sinoatrial node. Its electrical footprint is so small that it doesn't even register on the standard surface tracing. But as that signal travels into the atrial muscle, mass depolarization occurs. This coordinated cellular event maps directly to the first bump on our grid, the P wave. The signal then hits the atrioventricular, or AV node, which intentionally slows conduction to allow the ventricles to fill with blood. On the ECG, this physiological delay appears as the flat isoelectric line following the P wave. Once past the AV node, the signal accelerates drastically, racing down the bundle branches and into the Purkinje fibers. This triggers the massive synchronized depolarization of the ventricular muscle. That dense wall of electrical activity correlates exactly with the sharp, high-amplitude QRS complex. The horizontal axis of the ECG is a strict measure of time. It sequentially maps the firing of distinct cellular populations as the signal moves from the top of the heart to the bottom. After the ventricles contract, the cells must reset. This period of ventricular repolarization creates the broad, slow curve of the T wave. This chart breaks down the critical measurements on that timeline. The orange bracket highlights the PR interval, defined strictly as the time from the onset of atrial depolarization to the onset of ventricular depolarization. The red QRS duration measures the exact fraction of a second it takes for the entire ventricular muscle mass to fully depolarize. And the blue QT interval represents the total temporal footprint of ventricular activity, from the first spark of depolarization at the Q wave to the final moment of repolarization at the end of the T wave. If that QT interval is prolonged, the cell's relative refractory period is stretched. This extended vulnerability window can trigger lethal arrhythmias. These intervals are the strict speed limits of the heart. Any deviation along the horizontal axis pinpoints a roadblock somewhere in the conduction pathway. Time is only half of the diagnostic equation. To understand why a wave points up or down, we look to the vertical axis, voltage amplitude, measured by spatial recording electrodes on the body's surface. A wave of depolarization moving directly toward a positive electrode creates an upward positive deflection. Conversely, if it moves away, it creates a downward negative deflection. Repolarization carries the opposite charge, so the rule inverts. A wave of repolarization moving away from the electrode produces a positive deflection. This explains why T waves are typically upright. The morphology of these waveforms is never arbitrary. It is a strict geometric calculation of an electrical vector relative to the observer's physical location. This image displays the anatomical placement of the 6 unipolar precordial leads, marked by the red dots rather than around the ribcage. These form our horizontal, transverse plane of observation. When combined with the limb leads, this exact anatomical placement generates 12 entirely different perspectives of the exact same electrical event. Apply our vector rule to lead AVR, which sits up on the right shoulder. The bulk of a normal heart's electrical mass moves down and to the left, which is directed entirely away from AVR. Because the primary vector is moving away from that specific camera, the P wave, QRS complex, and T wave must all present as negative deflections in a normal AVR tracing. Now shift your attention to the left ventricular leads, V4 through V6. Notice the tiny initial downward dip, the Q wave. This represents the brief moment of left to right septal depolarization, which moves briefly away from these left-sided electrodes. This dip is immediately followed by a massive R wave. This is the electrical signature of the thick left ventricular wall, depolarizing directly toward those same electrodes. The 12-lead ECG functions as a network of 12 cameras, photographing the exact same electrical storm from 12 precise, verifiable angles. We can distill all of these vectors down into a single measurement, the mean electrical axis. This represents the average overall three-dimensional direction of ventricular depolarization. Look at section B of this diagram. We can calculate this axis mathematically using the frontal limb leads. First, we take the net positive amplitude of the R wave in lead I and plot it directly along the horizontal axis. Next, we take the net positive amplitude of the wave in AVF and plot it along the vertical downward axis. Drawing the resulting hypotenuse between these two coordinates gives us the precise angle of the heart's electrical axis. In clinical practice, there is a faster diagnostic shortcut. The mean axis will almost always lie exactly 90 degrees perpendicular to the isoelectric lead, the lead where the positive R and negative S waves are of exactly equal height. Calculating this geometric vector helps identify specific pathologies. A significant axis shift can indicate underlying issues, such as a conduction block in a bundle branch or the physical enlargement of a ventricular wall. This hexaxial wheel maps our final calculations back onto the human torso. We have followed the process from a single microscopic ion flux to a physical voltage vector, and finally to a global clinical measurement pointing firmly into the normal quadrant. These shifts in timing along the intervals, or spatial changes in axis deflection, provide a primary diagnostic framework for assessing cardiac integrity. By applying these first principles of physics and anatomy, the flat, static lines on the grid vanish. What remains is a direct, real-time window into the living biomechanics of the human heart.